Hello students, today we will discuss about equation of our magnetic dipole moment because of electron. So um, from electrons rotation we want to find it out magnetic dipole moment. First of all, that is a very primitive equation. You are aware about whenever current is passing from any type of current carrying wire, it is producing magnetic field. Same is the course you have. Whenever you have electron, then electron is also producing you that magnetic dipole moment. So first of all, we are dealing with the such type of a circular figure which has been given to us, or you can just assume that is called as a ZE, and this is my radius, and here my electron is revolving in circular fashion. This is the first theory which has been proposed by Niels Bohr in 1911. So you may be aware about because of this proposal, we will just derive that expression, and which is also correlated with one more equation or value. And because of his contribution in a such type of proof, we will just use another type of unit. First of all, you are aware about that our charge of electron is revolving around it's a circle, so it is producing current. So I have that q equals to it, and you are aware that omega is equals to 2 pi by t. I am just double implies 2 pi by omega. So this is the equation number second one. Place in the first one I have my current, which is in terms of e omega divided by 2 pi. This is the very initial expression I have from my current. You can directly use this one. I want to correlate this expression in the term of magnetic dipole moment, and you are aware that magnetic dipole moment m is equals to ia. I have my radius is called as a capital R, so I may place that magnetic dipole moment is I into pi r square. So from a is been placed in this expression, I may get magnetic dipole moment is called as e omega divided by 2 pi into pi r square. So it double implies my magnetic dipole moment as e omega r square divided by 2. This is the expression which I am in a need of. So in some of the MCQs we will use such type of expression. How to derive magnetic dipole moment. Instead of omega you can place 2 pi f as well. I want to correlate this expression with the call as angular momentum. So you are aware about angular momentum in your 11th science, that L is equals to I omega. Let's say I'm just naming it as equation number third one. And I, you are aware about the value of I, that is called as our moment of inertia. So it is called as a moment of inertia, and inertia of, I want to just say that it is for the ring. Moment of inertia of a ring is called as mr square. I am placing this value in the previous part. So my angular momentum L will become moment of inertia is called as mr square into omega. Don't confuse, because I is also current, and this I is called as a moment of inertia, that previously I was current. So be careful whenever you are putting such type of values. I have this one equation, so I am just putting this one as, let's say, my equation number B, and this is my equation number C. So I am just taking the ratio to prove that my gyromagnetic ratio to equation number B divided by equation number C. I am having m magnetic dipole moment, and L is called as my angular momentum, e omega r square divided by 2 and whole to the base mr square. So I may get e divided by 2m. So this is the equation I have. This is my mass, so I'm just putting that small m. So to just prevent our any type of doubt, I'm also putting that my small m over here. So my 2m is left, it is called as my mass. So my equation I have left is called as a charge to mass ratio, is called as a m by L, that is called as a gyro magnetic ratio, or its another name is called as a charge to mass ratio. So we have E divided by 2me. This is the primitive equation we had. Now I am putting their values, or finding it out m by l, or you can just say that the gyromagnetic ratio's value 1.6 cross 10 to the power minus 19 coulombs. 2 is okay. Mass of electron is 9.1 cross 10 to the power minus 31 kilograms. So it may give me 8.8 cross 10 to the power 10 coulomb per kilogram. Be careful whenever you are finding it out, so it's a value, because such type of a 10 to the power 10, or if you, some people are just doing a round it off to the 9 cross 10 to the power 10 is a unit coulomb per kilogram. It is the value of m by l, or call as my magnetic dipole moment to the momentum ratio, angular momentum ratio, or gyromagnetic ratio, or charge to mass ratio. Some people are in hesitation or in a speed putting that 9 cross 10 to the power 9. It is something else. So be careful whenever you are dealing with this such type of units. Now what I want to just find it out is another relationship. You will be aware about such type of formula, that is called as angular momentum is directly proportional with the my Planck's constant h and number of orbits divided by 2 pi. It is our equation of a Planck, or angular momentum. So this is the equation valid in a quantum physics, but this equation we will learn in a chapter number 12, when we will just discuss about our L equals to nh upon 2 pi. I want to utilize this expression. So previously we have m by L is equals to E divided by 2me. This is also angular momentum. This is capital L I have placed. I am putting this value, so I can have m by L, that is called as nh divided by 2 pi. So my equation will lead me to E upon 2me. So my magnetic dipole moment m is equals to cross multiplication and arranging these terms, E upon 4 pi me multiplied by h. This equation is called as a Bohr magnetron equation, or is this m is called as a m minimum. It is called as a minimum value of magnetic dipole moment. Now why we are calling it as a magnetic dipole moment's minimum value? So first of all, we are putting those values over here. You are aware about some of the values. Let me remind you, h is called as a Planck's constant, 6.6 cross 10 to the power minus 34 joule into second. So I'm just mentioning that its unit is called as in terms of SI. Following all those values in the above expression, m is equals to 1.6 cross 10 to the power minus 19. H is a Planck constant, its value is a 6.6 cross 10 to the power minus 34. 4 multiplied by 3.14. Mass of electron is 9.1 cross 10 to the power minus 19 coulomb. It contains the same unit as our magnetic dipole moment. So you may get that value 9.27 cross 10 to the power minus 24. The unit of our magnetic dipole moment is called as ampere meter square. So this is the value of a Bohr magnetron, or it is called as a minimum value, m minimum. So such is the value you have to utilize and you have to remember, because in school or maybe sometimes in MCQs they are asking that what is the gyromagnetic ratio, or called as a charge to mass ratio, what is the unit of it, what is the dimensional configuration of it. Now you are aware about its dimensional configuration. Its dimensional configuration is nothing new for you. It is directly, you can just place that m minus 1 L0 T0 and Q1, or you can just say that m minus 1 L0 T1 and A1. So this is the ratio of gyromagnetic ratios, unit or dimensional configuration values, and this is the value of Bohr magnetron. In exams they are asking that what is the value of Bohr magnetron and what will be the unit of it. So this is the Bohr magnetron's value is 9.27 10 to the power minus 24 ampere meter square, and this is a gyromagnetic ratio. So after that theorem, you are now quite comfortable with how to just to find it out, the ratio, charge to mass ratio, or deal with the electric dipole moment for electron. In the next word we will just discuss about some of the application related to it. Thank you.